Here is basically a system of linear inequalities that we want to solve. Just like the one that we did over here. However, you'll notice here there are 4 inequalities. So what we're looking for is the feasible region that will make all 4 of those inequalities true at the same time. One of the first things I want you to recognize is the way that I drew my graph. You'll notice that I drew just a first quadrant graph. As you mentioned, there are 4 quadrants. First quadrant, second quadrant, third quadrant, fourth quadrant. Can someone tell me why I only drew a first quadrant graph with this particular problem?
Because with your x and y have to be greater than 0.
Yeah. X has to be greater than or equal to 0. Y has to be greater than or equal to 0. The solution must be in the first quadrant. It doesn't mean your graph can't extend farther than those quadrants. The solution has to be in the first quadrant. Does everybody understand why? That's a very important concept. Good? Okay. Now, next thing I'm going to do is I'm going to go ahead and graph these 2 inequalities. Basically, I already have these done. X is greater than or equal to 0. Anything to the right. Y is greater than or equal to 0. Anything above the x-axis would be shaded. So if I was going to stop just with those 2, this would be the region that would be totally shaded. Is everybody okay? But we have 2 other lines we have to be concerned about. This one I'm going to graph just using my x and y intercepts. Now, if you are a slope-intercept person and you need to put it in the slope-intercept, you go right ahead. I'm going to do it the simplest way that I possibly can. If I let my x be equal to 0, my y-intercept would be 0, 2. So I've got 0, 2, which is right here. There's my y-intercept. To find the x-intercept, I'm going to let y be equal to 0. So I'd have 2x is equal to 6 and x is equal to 3. 1, 2, 3. There we go right there. Got that taken care of. So there's my line, and I'm going to go ahead and connect those 2 points. And when I do, I get a line that looks just like that. That's the easiest way to go to graph that line. Now, my second line, I can't do that because 6 is not divisible evenly by 4, so I have to put that in the slope-intercept form. So I have y is going to be less than or equal to negative 4x plus 6. 1, 2, 3, 4, 5, 6. Here's my y-intercept. My slope is negative 4. I'm going down 1, 2, 3, 4. I'm going to go right 1, which would put that point right there. I'm going to connect these 2 points, and when I do, I get a line. It's going to look, let me turn this around here. There we go. The line that looks just like that. I'm going to label that line. This again is y equals negative 4x plus 6. This line right here is going to be 2x plus 3y is equal to 6. So I've got the lines graphed. Got the lines graphed. Is everybody okay? I'm just graphing the lines. Nothing to it. We've already done it. That's what I said before. Got to make sure you remember how to do all of these things. Once again, these are both less than or equal to. Here is this line. There's a region clearly above. There's a region clearly below. We would shade the region below that line. Everybody good? Here's this line, 2x plus 3y. Again, that's less than or equal to 6. I would shade everything below that line. So if I'm looking for the feasible region that's going to make all of those inequalities true at the same time, it would be located right there. That would be the area that contains all of the points that will make all 4 of these inequalities true at the same time. Has to be below this one, has to be below this one, has to be to the right of this, has to be above this. That's the region that would contain all of the points that make all of those true simultaneously. Is everybody okay? Okay. Now I'm going to add a portion to this problem. This is the same thing that we did over there. If we were going to just solve a system of linear inequalities, we would be finished now. That would be our answer. That would be the feasible region. That would be the feasible region. But I'm going to add something to that. And I'm going to add we want to go ahead and maximize z equals 5x plus 2y subject to. Now we've turned it into a linear programming problem. What we're going to be looking for are the values of x and the values of y that are contained in this feasible region, that when I plug them into this function right here, it will give me the largest value possible. This function right here is called your objective function. That is going to be one of the most important functions that we deal with when we're dealing with business problems. That's going to be maximize profit, minimize cost. Those are areas that we're going to be dealing with. That's what that objective function is going to be. It's what you're trying to accomplish. This subject to, these are called constraints. Those are areas in which you have limitations. For example, you're trying to go ahead and minimize or maximize your profit in a particular industry, but your constraints are going to be the amount of times you can be on machine A, the amount of time you can be on machine B, could be the amount of workers that you're going to have, whatever the situation might be, there are going to be constraints. You can't just go ahead and manufacture as many things as you want to in any given business situation, so there are constraints. That's what these are. Okay? So what we've done so far is we've really taken care of one of the most critical areas of the problem. We've already come up with our feasible region. Here's our feasible region. Now, there are basically an unlimited amount of points that occur in this feasible region. We need a specific number. We need a value for x and a value for y that when we plug it into this objective function, it will give us the largest number possible. Well, the way that we're going to do that is we're going to do it through something which is called the corner point theorem. The corner point theorem. And I'll tell you all about corner points in just a second. The corner point theorem says that if a maximum or minimum value exists, it must exist at one or more of the corner points. Corner points occur at the intersection of the lines that create the feasible region. Corner points occur at the intersection of the lines that create the feasible region. That means a corner point is going to have to touch the feasible region. So, taking a look here, we want to identify our corner points. Would that be a corner point? No, not a corner point. Is this a corner point? Absolutely. And this corner point is 0, 2. Is this a corner point right here? Yes, definitely a corner point. That's 0, 0. Is this a corner point out here? No, it doesn't touch the feasible region. Is this a corner point right there? Yes, it is. Is there a corner point right there? Yes, it is. Now, just like before, we'll notice that this corner point right here does not look like it falls on a whole number. Neither does this one right here. That's why we spent as much time as we did in Chapter 6 on being able to go ahead and solve systems of linear equations using elimination. We have to find out what the coordinate of this corner point is. That might be the answer to this problem. Because if we have an answer to the problem, it has to occur at one or more of the corner points. Well, we know two of them. We know two. And we know one can't be the answer. You can't possibly get a maximum value if you plug in 0, 0. So first of all, we're going to look for this corner point right here. This corner point occurs at the intersection of this line and this line. Well, the equation of this line is 2x plus 3y is equal to 6. The equation of the other line is 4x plus y is equal to 6. And again, I'm going to go and use elimination, which we just did on the last test. I'm going to multiply this equation by -2, get rid of the x's. That gives me negative 4x minus 6y equals negative 12. 4x plus y is equal to 6. I get negative 5y is equal to negative 6, and y is equal to 6/5. So the y coordinate of that corner point right there is 6/5. We need to find out what the x coordinate is. Now again, can you take 6/5 and plug it back in? Sure, if you're good with fractions. If you're not, you don't have to be. We'll just resolve it just like we did in the last chapter. I've got 2x plus 3y is equal to 6. 4x plus y is equal to 6. I'll multiply this equation by -3. I've got 2x plus 3y is equal to 6. Negative 12x minus 3y is equal to negative 18. Gives me negative 10x is equal to negative 12. And x is also equal to 6/5. So that corner point right there is 6/5, 6/5. Yes?
Why couldn't you just put the y in to be like 4x plus 6
Oh, you can, if you want to work with fractions. Some people tried to do that in the last test. It was a disaster. Okay, so I mean, if you can work with fractions, that's fine. If you can't, you can resolve it. Personally, I would plug them in. Okay, I would plug them in, but there's a lot of people that can't. So this is what, does everybody understand what she's asking? You could just go ahead and substitute that in, 6/5 for x, and then go ahead and solve it for y. That's fine, as long as you can work with fractions. Right? So we found this corner point. We've got one more right here. This corner point right here occurs at the intersection of this line, which is y equals negative 4x plus 6, and this line right here, which is going across the x-axis, which has to have an equation of y equals what? 0. And y equals 0. So I've got 0 equals negative 4x plus 6. Negative 4x equals negative 6. X is going to be equal to a negative 4/6. Okay, negative 4/6 turns out to be what? Or 6/4. Some say 6/4. Turns out to be 3/2. So this corner point right here is 3/2, 0. So we found all 4 corner points. Now what's important again about this theorem is we need to find the value for x and the value for y, that when we plug them into the objective function, it will give me the largest number possible in this feasible region. Even though it's contained, there are a zillion different combinations. So we have narrowed it down from a zillion, okay, down to 4. So what we're going to do now is we're going to take those 4 corner points and we're going to plug them into our objective function. So I have z equals 5x plus 2y. We're going to plug in 0, 2. We're going to plug in 3/2, 0. We're going to plug in 6/5, 6/5 There's no reason to plug in 0, 0. That cannot possibly give you a maximum value there.